your video on, I think.
We're just leaving the thing open in the background.
Oh, okay.
So we can see the screen.
Okay, okay, yeah. Yeah.
Okay, so shall I start?
Yeah.
Okay, excellent. First of all, I would like to thank John and Transport Education for giving me this option, this opportunity.
Are we all right?
Yeah.
So, and especially John, that you're here now. It's in the middle of the night for you, right? So,
Yeah.
I think so. Thank you, and I'm very happy that I have this opportunity to speak here, and I think it's a very good idea, and I think it should be done much more. So, my name is written over here, which is a complicated Dutch name, so just call me Peter. And today I will talk a little bit about pattern formation, and especially pattern formation with a small parameter. So, before we start, I don't do this on myself. I work with a lot of people in the US, in the Netherlands, and in Japan. And these three people on the screen, I call these the group of 64 because they're all born in 1964, and they are my advisors. The two to the right are my postdoc advisors, and the one on the left, that's Arjen. He was my PhD supervisor. And then in the bottom, this whole list of people are the people who I'm working with or have been working with. So before we start, let's talk a little bit about myself, right? So this handsome guy on the left is me. I'm married, so that's okay. So I did my PhD in Amsterdam, which I finished in 2009. And then I did 3 years of postdoc in the US, on the East Coast. And then since August of this year, I became a lecturer at the Queensland University of Technology here in Brisbane. Excuse me. So, QUT is a university which slogan
Yeah.
Yes.
Can you see the screen?
Yes.
Okay, excellent. So, that's not one I would say, right?
Yes.
So QUT is a slogan used for the world. So they have a very link with industry. There are also a lot of international students. I think 1 out of every 7 students is international. And they try to get a lot of international students. For example, they also have a representative in Accra and Ghana, where you are, right? So, there are always opportunities to come here. If you want to study here, there are always possibilities. There are always ways to get here. So this is a little bit of advertisement for my university. And let's now start the real work. So, today I'll talk about pattern information. You can talk about pattern information without talking about Turing patterns. And I also understood that you are reading a paper on Turing patterns at the moment, or some of you, which is doing Turing patterns in the growing domain. So I will give a short introduction to Turing patterns, but I will do it quick and dirty version, so easiest case. Then I will go into a direction which is more my expertise, which is far from dynamics. So Turing patterns are patterns which have a simple amplitude, and I'm more interested in patterns which have a big amplitude. So I'll introduce the model which I'm mostly interested in, and then I will give you results about existence, stability, and interaction. And instead of proving these results, I will try to describe methods I use to prove these results. So I use numerical simple perturbation theory for the average function, organization methods. So I will try to give easier examples of how these methods work, get an idea what's going on for the more complicated system. So if there are any questions, please do interrupt me, right? That's why we are here. So if you have a question, please help me try to answer it. So veterans are everywhere, right? If some here on the top left, we have some sand dunes of the Sahara Desert. Then on the right, we see zebras and I think it's I don't know. It's a pendrel. I don't know. Don't put me down on that, but you see zebra days, stripes. This animal and this other animal, this is spots. Although they're not animals, they're different patterns. And here on the left bottom, you see on the coast islands, also exponential patterns on the coast. So these patterns are everywhere, right? And zebras and sand dunes are of course different. If you see the same sort of stripe solutions. And we also see the same sort of what we call defect solutions, or what I call defect solutions. Here, we see two stripes coming together, and teaming as one stripe. We see something similar here at the zebra, where you have two stripes, which then align and become one stripe. These are the things I can describe what's going on here. A little bit more pattern information, which is already more in direction what I'm doing. Here on the top left, you see vegetation patches. This is vegetation which you see on the border between the desert and where there's a lot of vegetation. So these patches are about 20 centimeters in size. And you see sort of spots and these what I call wings. They sort of indicate when a vegetated piece of ground becomes a desert. So this sort of people claim these are sort of criteria for when land becomes a desert. So these are important. Here on the top left and on the bottom left, we have sand, let's say on a table, and then you start shaking the table. And if you do this in the right frequency, you see these localized bumps of sand coming up and then coming down. So the sand is not coming up, everything is not coming up and coming down, but you have these localized structures which come up and come down. And here on the right, you see something similar, localized structures, but now in fluid, which are made magnetic. It's very expensive fluids, and if you put a magnetic underneath them, they will become magnetic charged, and you can make these solitary solutions. These are the solutions which I'm interested in, these small localized solutions. But as I said, we cannot talk about temper, we talk about Alan Turing. Alan Turing lived in the beginning of the 1900s. In 1952, he wrote one paper on pattern recognition. He actually only wrote one paper in his life on pattern recognition. So this is the same Alan Turing with no Turing machine, and he wrote one paper on pattern recognition, and it happened to become the one paper in pattern. So this was a really smart guy. So what was his idea? His idea was if you have an ODE, which is, let's say, a stable unit of states, stable, can we make this unstable when we execution? This is sort of counterintuitive, because when people thought of diffusion before, they always assume it had a stabilizing effect. If you, for example, think of the equation, if you give the delta initial condition, let you use, it will make everything equal, right? So always thought that diffusion stabilizes things. But it turned out that diffusion can also make something stable unstable. And nowadays we call these Turing patterns. So let's do the quick and dirty version of Turing patterns. So we have an ODE, a kinetic system, which is given over here, and it turns out that at least we need to have a two-dimensional system, so with a U and a T, and we have some nonlinear terms on the right-hand side. Now what we want is that the origin, let's say, is a stable fixed point. So what do we need? So what do we do? Well, of course, yes. For one there it is. So we go linear, right? We determine Jacobian, which I denote by capital A. Then we determine the polynomial and see when we have and determine the eigenvalues. So this is more or less goes down of substituting in e to the power lambda t. And if the eigenvalues are negative, they're stable, if they're positive, we know that we are unstable. And then we recall from algebra that the trace of the Jacobian is equal to the sum of the eigenvalues. The determinant of the Jacobian is equal to the product of the eigenvalues. So if we want 0, 0, 0 to be stable fixed point, the sum of the eigenvalues needs to be negative, and the product of the eigenvalues needs to be positive. These are two conditions for Turing instability. We want that 0, 0 is a stable fixed point over the E. So the derivative f with respect to u plus the derivative of g with respect to the second p should be negative. Well, their product should be bigger than f with respect to p times g with respect to u. These are the conditions under which 0 is a stable fixed point. So now we add diffusion. So we add the diffusion to this equation, which we have added over here. And as it will turn out, the diffusions cannot happen on the same with the same constant. So we need to add this red d over here, because otherwise we will not be able to create Turing. Now the question is, by adding this diffusion, can we transform our fixed point to become unstable? So we proceed in the same way. We first linearize the equation, but we still have Laplace W in here, right? And now D is the diagonal matrix with the diffusion coefficients. Now what to do? Plug in. Before we can determine the correct polynomial. Now in terms of the wave number. So the correct polynomial is now given by the expression over here. So 0 should be equal to the determinant of this expression over here. But K is now the wave number. So think of it as going into the A space. So if 0, 0 wants to be stable, the eigenvalues of this matrix is negative f k you can choose. So we do the same trick as before. You know the sum of the eigenvalues. Trace. So if you could do the traces, you get lambda times 2 plus b minus k squared times 1 plus b. And the product is the determinant, which I've written down over here. So let's see what we have now. We already know that our ODE was stable, so we already had to assume that FU plus GP was negative. So this term for the PDE is negative, and we subtract something more. So we already know that the sum of the eigenvalues for the PDE system is always negative, independent of what k is. It doesn't matter what k is, 0 or minus 5 or 25, it will always be negative. The sum of the eigenvalues is negative. So if we want this to be unstable fixed point, we have to find k such that the product is also negative. That means that one of the two has to be positive. So the product number 1 times number 2, which I've written down again over here, and then work it out, so write it down slightly different, has to be negative. This first term is positive, because by the second condition, d times k to the power 4 is also positive. It has to be positive. This negative term has to be negative, but it's always negative. So d times fu plus gp to be bigger than 0. This is the third condition. If you look at the first condition, fu plus gp has to be negative, d times fu plus gp has to be positive. So we cannot have d is equal to 1. So this is why we needed to use the g and the b in the beginning. So this is the first condition. Now, last condition satisfies. We have to make sure that this polynomial becomes negative. Well, this is just second order equation in k squared. So we can just include when we have, let's say, when the polynomial process 0, which is given over here. So just it looks like a little bit like b squared should be equal to 4 times a times. This is just a quadratic equation. So what we now have derived 4 conditions for Turing instability. And this is again, this is one dimension, we don't have the main row, we just have an infinite domain. This is the most easiest case. We have these 4 conditions, and if our system fulfills these 4 conditions, and we know that Turing is. sort of a right? We have this D, we have the derivative of F with respect to two variables and G with respect to. So we can definitely realize this. So we have now constructed, let's say, an example where we can show the distribution can have a stabilizing effect. And this is Turing instability, and this was the main important word for Helen Schumann. So let's do short example. So I sometimes put in empty slides. If there are questions, I hope that I can write on this slide to answer your questions. It will not be easy for me, but it will be something like this. Are there no questions at this point? So we just continue. We continue. Exactly. An example of instability, but now it's 2D, is this Swift-Holman equation, which is a very well-known equation. And this is presumably modeling this densification I was talking about in the beginning. So this creation of deserts in these spots and stripes. I did not make this move myself. I got this move from David Lloyd, who is at Turing University in England. Okay, I see you okay, perfect. So I would like to thank David for giving me this move. So you can now click on movie 1 on the Vimeo account. You will see. You see that we get stripes and we get these spots. So I will continue. So I go to the next slide. Give rise to small and so we have the backup state. Just slightly disturbed, and we get feathers which are have not a big end. I'm more interested in things which have big ends. So I'm more interested in the following type of question. And again, this move I have not made these moves myself. These moves are made by Professor Nishira, who is in Sendai in Japan. So if we click on copy 2. You see here is a 1D simulation. We'll skip the movies. So what we will see in the movies, I sort of explain this on the next slide. This is on that time run. Even on that time these two pulses move towards each other, they collide, and then they disappear. If I now slightly change my parameters in this system, what I will see, take the same initial condition, we still see that the solutions move towards each other, they collide, then we have to wait very long, but in the end, one of them actually sort of survives and starts moving again. So these two movies are just for slightly different So these are the type of questions which I'm interested in. And these simulations are actually done for a specific model. And this model was derived in the mid-90s. The group of Professor Permans in Münster, Germany. So what they have is they have two class plates. This is a sketch of the setup. So they have two class plates. Between they have a noble gas. And they apply a voltage difference over here. And this is just a camera and some other optical stuff. And then they observe these type of patterns. Just have to think of if something is dark, let's say in one state, and if it's white, it's in another state. You see, they see these stripes. They see these spots, and they see sort of rings, and they see this checkerboard. So, the first attempt to throw down a model bit, which was of the following form. It was a couple of PDEs. Where epsilon here is a small parameter. And if you for the moment forget about this, for the epsilon, so this small quantum term. So if you forget about this term, can you determine the fixed points for this system? 1 and 0, 0. 1 at 0, 0, 1 at plus 1, plus 1, and 1 at minus 1, minus 1. And you can obey, let's say, at the Turing test. But it turns out, 0, 0 is not even a stable point for your kinetic model.
So, Peter, I had a quick question. So, the reason why the epsilon is strictly less than 1, is it because does that help guarantee a fixed point because of the contraction map theorem in a way, or?
No, so why we take epsilon to be small? Why we take epsilon to be small is in a lot of biology, thingies. Concentrations diffuse and the species diffuse on a different scale. So quite often, this is like 10 to the power 5, if you determine a ratio, 10 to the power 20, or 10 to the power minus 10.
Okay.
So it's reasonable to take one of them to be small. One to be small. So you just have one species really fast, another one moves sort of slow, diffuse very slow. But I will come back to this a little bit later. But the main point I want to make here for this model is
We're now muted.
we have this model, we have this PDE, but if you see patterns, they're not Turing. But if you see patterns, they're not Turing because they don't fulfill the Turing. If you see patterns, there's something else. So if you see patterns, there's something else. This was the first attempt for the model. To describe what's going on in this gas-discharge experiment. But it turned out that this was so simplified. So this is, let's say, so it was too simplified. So this is the real model, because it can definitely not describe the real world. But this is a good approximation. So I will go into details on this model. On the next slide. We call this a generalized Turing equation. So we have active things, we have inhibitors, and it's a bistable. There are a lot of conditions on the parameters. If you saw these pictures from before, you sort of have to think the U model, sort of the current density. The model P model, voltage drop over the W model plus plane, and W models will serve. And in these pictures, more or less, they plot U. Let's say black means used into minus 1, which is one of the stable states of your system, and white means U is plus 1, which is another stable state. If you do simulations, let's say in 1D, you just take this model, plug it into your machine, you find, let's say, stationary solutions. Which have sort of this form. And here you see that this different scale. The U component is very, it's more or less looks like a shot, but it's actually very sharp outward edge. And the C and W are much slower. So we have multiple scales. So we are mathematicians, right? So let's look a little bit more into the model. And I use different color. Probably U, P, and W, they do something. Let's first look at the UE component. So U, we also call this the activator. Or in the middle we call this the fast component. So it has a small diffusion. So there's an epsilon is something small, right? It's a very small diffusion. So if you start with something peak, it will stay peak for a long time. And you take a close look at this model, you can actually see that this is a perturbed Alencanic. You forget about this coupling over here, this is actually the Alencanic. The Alencanic equation is a very well studied system. This is a bistable equation of plus and minus 1 are stable. And we also know waves which are moving slowly. It's a force non-linear. It's a force non-linear. Because he also realizes that the coupling the feeds W to these vectors, the feeds W are small because of epsilon. So maybe we can use information about the Alencanic equation to study our whole model. How do we look at the red terms? We call the slow components. Also the inhibitors. They are at 4 to 1 diffusion. So D is just a constant which is 4 or 5. Let's say 2 or 4 or 5. They sort of diffuse on the same scale, but they diffuse much faster or much slower than the U component. Use a different scale. So therefore, use a different scale. So besides that, they're just linear. Besides that, they're just linear. Right? So we can solve them, right? There's linear equation. And they're not talking directly to each other. And they're not talking directly to each other. P doesn't talk to U. P doesn't talk to W. The only connection is that they both talk to you. So they're only indirectly talking. So maybe we are lucky, right? Maybe we are lucky, right? Again, an empty slide, but I see there are no questions so far. So maybe we are lucky. Maybe the equations, let's say, maybe the equations are still simple enough. So the singular term, the linear, and also the linear term is not too hard. Also the nonlinear term is not too hard. So maybe the equations are simple enough to do real math. And also, the equation is still complex enough to see what I would call interesting dynamics. So the equations are easy enough to stop, but they are still complex enough to not be true. However, not all the results I presented today are correct. Some are you can have formal, votes only, but they are formal. Votes only, but they are formal, which means that you make just let's say the higher order terms. And so for example, this movie which you played before, where we had these two initial conditions, these two pulses which move to each other and die out. This is not understood completely. So, what are the questions that we want to ask? We want to construct localized structures. So these are the structures which have expression in a small region, and in the rest they're sort of. We want to do this in 1D. So we want to do this in 1D. So we call this pulses. When we have spots, we want to do this in 2D. When we have spots, we also have stripes. These are existing. So can we they exist? After that, it will be if you can see, can we prove whether they are stable? Do we see them in real life? Do we see them in real life? Do we see them in nature? Finally, if you let's say have several of these localized structures, what happens if you put them next to each other? Right? How do they start talking to each other? How do they interact? And a more broader question, a more philosophical one, what is the influence of this second inhibitor? Influence of this W equation. Influence of this W equation. It appears to be similar to the other inhibitor. What is the effect of the W equation? What can we do with the W equation? We forget about W. So let's forget about W. So let's forget about beta equal to 0 and just forget about W. Other things which you can do with this. More extended model, if we cannot do with this easier model, of course the answer will probably be yes. Otherwise we'll not be studying it. But I really is not clear, right? Because these equations are, as I said, very, very simple. These are the type of questions I want to ask. Now I will come up actually. A lot of the results actually. And we will go over and discuss how to prove. First, some results in 1D. So now the space is 1D. Now Laplace U just means UX. What we can do, we can construct stationary pulses and stationary pulses, and we can determine whether they are stable or not. And moreover, we can also explicitly determine their width. So we can determine how we can determine the distance between the front of view and the back of view. We can determine this. This is all of course in leading order. But then we know that it's real results, so we know that it's real. And here is an example. Of a pulse which is traveling to the left. Sometimes I draw all the components. Sometimes I only draw the U component because this is easiest for the eye. Let's say the other two components in here, you will not be able to see. There's some more results in 1D. So we can construct. This is what they call a so-called two faults. So you see here we have two bumps in use. So I call this two faults. We can construct this and we can determine it. This is an example of a result where we really need this first component. So we really need this first equation. Without this beta equation, so when you set beta equal to 0, you cannot construct this solution. Third component really call this, in our terminology, we call this semi-strong interaction. Because if you look, for example, at the U, these two U bonds, here in the middle, this U is actually in sort of in a rest. So these two U bonds don't seem to be talking. Only if you look at the other square components, you see here in the middle, they're not at rest. They're not around -1. They are negative, but they're not close to -1. U, this U bump to the left, is talking to the U bump to the right, indirectly to P over here. They're not close to each other, the U bumps. They're not close to each other, the U bumps, but they're also not far apart. Because this is called semi-strong. So this is called semi-strong interaction. Now we have these different structures. Now we have different structures, right? Now we can, let's say we have a stationary and we have the shape of the pulse because we have the shape of the pulse because let's now say we make the shape of the pulse, we make the width, let's say, twice as big. So instead of M, we make it bigger. Let's say so 200, we make it bigger. 400. We let tiny fall. You see what's happening, right? You see what's happening, right? The width between the two pulses just goes to the stationary. What we expect, right? We make it a little bit bigger, but it's stable. Make it a little bit bigger, but it's stable. So maybe now make it even a little bit bigger. Maybe now make it even a little bit bigger. So instead of 400, 475 initial width, then you see they repel each other, and they sort of they diverge and they move off to infinity. How can we understand what's going on here? Can we describe what's happening here? Can we describe what's happening here? I mean, it's of course from an ODE point. Clear what's going on, right? In between these two solutions, which is a stationary solution, will be unstable. What can we prove now? What we want to do? Now, what we want to do? Is we're going to derive an ODE. We started with a PDE doing this. So what we want to do is we want to derive an ODE. Which describes the width between the front and the back. Here we see what's going on. So we start with an initial condition which has the width 400, which is actually M, goes to 100, which is actually M, it's 100. But if we start with something which is slightly bigger, we actually see that there's an unstable solution in between. So we this is what's going on, but how do we derive this ODE, right? That's the main question. Also in 2D we have a lot of results. These are a lot of movements between our columns. I think 7, but we will sketch this movements. So I will just stop. So you can construct spot solutions. So spot solutions are, let's say, Aurelius solutions. So the Aurelius can still, let's say, transform our two-dimensional PDE to we can construct this stationary scalar solutions and we can determine the Taylor field. And then we can also make this so we can sort of give them a little bit push change some of our parameters and then construct traveling spots which also turn out to be stable. This is one of the main goals. I wanted to find these traveling stable spots. In reaction diffusion equations, people always if you only have two coupled PDEs that you cannot create unstable spots. Now we have three components, so maybe we now construct them over here, and it turned out yes. So we have these spots, we can make them. We also have, let's say, fronts. This is just a solution which is minus one in one part and plus one in the other part, and just a straight line in between. Let's say a generalization in one direction, just extend it in the y direction. We can construct response, and we can determine whether they're stable or not. We can also, let's say, put two of these traveling stones together, and then make them stationary, so we can construct stripes, determine their width, and we can show the stripes and spots actually can coexist, so they can live peacefully. With all these results in 1D, which are rigorous, and in 2D it's a bit more complicated, so some of the results we're talking about here are only the formal. More results, so we can also, for example, see what happens in something which looks like
here on the seabed. So if you have
deep
two straps
here on the
connected
seabed.
to
So
one
if you have
strap,
two straps
if
connected
you
to
put
one
this into our
strap,
model, you will
if
see
you put this into our model, you will see the defect is actually moved out.
not a little bit.
Not a little bit.
So are there any questions so far at this
Are there
point?
any questions so far at this point?
I think that if nobody's swimming, I guess
if nobody's swimming,
Yeah, I think we can move on. Yeah, I guess if they had a question, they probably would have written in the chat window. Or
Sure.
yeah, I think
So,
so.
yeah. But I will just give, so if no questions, really don't hesitate to ask, right?
Don't hesitate to ask,
Because
right?
information.
Because I know this is a lot of
Now
information.
go
But we will
a
now
little bit
go
into an analysis.
a little bit into
So,
the analysis.
and we do some easy examples. So,
And we do some easy examples. So,
if you are lost so far,
if you are lost so far, if you
this is
follow the one point, this is
let's say, again, start pay attention and see.
again start pay attention and see
what's going on now.
if you can understand what's going on now. Because it will become
So,
easier.
for the analysis,
So, for the analysis,
study the structure, we have
so what do we do to
main
study the
techniques.
structure? We have sort of
So
three
for
main techniques.
existence, we use
So
geometric
for existence, we use geometric single fluctuation.
Stability, I use the
For
x
stability,
function.
I use the Evans function.
However, I will not talk about that.
However, I will not talk about the Evans
It
today
takes enough
because
power to explain.
it takes enough power to explain a little bit about the Evans function to do this.
And for the interaction, we use the renormalization.
And for the interaction, we use the renormalization proof method.
So this is pretty hard for PDE analysis.
This is really hard for
But I will
PDE
give again an
analysis.
easy.
But I will give again an easy
Illustrate what's going on.
illustrate what's going on in renormalization.
So as I said, we got the two.
So as I said, we now do two simplified examples.
So we have this PDE, right?
So we have this
And we have
PDE, right?
PDE with an
So
epsilon.
we have this
small.
PDE with an
So
epsilon
we
is
want to use the
small.
fact that epsilon
So we
is
want
small,
to
so we
use the
set
fact that
epsilon to
epsilon is small.
zero.
So we want to set
Now that
epsilon
makes
to
our life
zero.
easier.
Because that makes our
And
life
maybe we
easier.
can get from the epsilon to zero.
And maybe we can
get
from the epsilon
some
to zero
nice
system, maybe we can get some nice approximation.
But there's always this problem, right?
But there's always this
Small
problem,
parameter can
right?
have the big
Small parameter can have the big impact.
For example, if we just think of two cubic
If we
polynomials,
just think of two cubic polynomials,
and we want to determine average.
we want to
So
determine
the
average.
first cubic polynomial is
Now
x
the
cubed
first
minus
cubic
x squared
polynomial
plus
is x cubed minus
zero,
x
where
squared
epsilon
plus
is
epsilon is
half.
equal to 0, where
The
epsilon
second
is
one,
half.
we just shift the epsilon
The second
to the
one,
highest.
we just shift
the
the
highest,
epsilon
uh,
to the highest
Now
term.
epsilon times x cubed.
Now
minus
epsilon
x
times
squared
x
plus
cubed minus x squared plus 1.
Now, of course, we can solve this
Now,
explicitly,
of
but
course, we
let's
can
say we
solve
don't
this
want to do that.
explicitly, but let's say we
So
don't
we
want
want
to
to
do
say,
that.
okay,
So we want to say,
what we
okay,
get when we set epsilon to
let's see
zero.
what we get when we
Our
set
life
epsilon
will
to
become
0.
easier.
Our life
We
will
still
become
get all our
easier.
information.
We will still get all our information.
So, we set epsilon to zero, right? In
Set epsilon to
this
0, right?
equation,
In
it will
this
become a
first
regular
equation, which will
And
become a
we
regular
get now
equation.
x cubed
And we
minus
see we
x
get
squared
now
zero,
x cubed
we can
minus x
explicitly
squared
solve
0,
without
which we can
any thinking.
explicitly solve
So we
without
find
any
two source
thinking.
solutions.
So we find two source
And one
solutions,
times
and one
root
times
will be one.
and one root will be
So
1.
we're gonna put on epsilon.
So we're going to put an epsilon and plus the real cube
reduced
polynomial
one,
and the reduced one, you see there indeed
close to each other.
Close to
for
each
this
other.
equation, that put the
So
epsilon
for this
to zero,
equation,
that
that
made
made
our life
epsilon
easier,
zero,
and
made our
our
life easier,
approximations
and
are.
our approximations are pretty decent.
Let's not do the same. The second
not do the
cubic
same.
equation,
The second
instead
cubic
of epsilon is
equation,
zero.
instead epsilon is
Here.
0,
C instead of cubic equation, we
C
now
instead of cubic equation, we now
quadratic equation.
Uh,
So we love
quadratic
we lose a root.
equation. So we lose a
Now
root.
if we now plot
So
the
if we now
approximation and the real equation,
approximation and the real equation,
it still
you
finds
see,
these two roots.
it still finds these two
right? And
roots
it's so
pretty
hold on.
decent, right?
And it
it's
doesn't find a
hold
root
on.
which is around
But it
10.
doesn't find a root which is
Now
around
what's
10.
going on here, right?
Now what's going on here, right?
Let's say that we didn't know what was going
Let's say
on.
that we didn't
So
know
this
what was
equation,
going on.
we say, oh,
We saw
epsilon
this
is small, so
equation,
we
we
can
say,
say,
oh, epsilon is small, so we can say to 0,
So
we
there
can
are
find two
But
roots.
this is of course
So
not
there
true,
are
right?
two.
Because we
But
know
this is
that
of
there
course
are
not true, right? Because we know that there are
So,
two roots.
for that reason,
So, for
because
that
this first
reason,
equation we call this a
we call
regular
this first equation, we
because
call
we
this
can
a
set that
regular
to zero.
perturbation, because
We
we
still
can set
obtain
that
all
to
our
0.
information.
We still obtain all our information.
And the second equation, the second
And the second equation, the second equation, we call it singular equation, because when we set epsilon to 0, we actually
don't
lose
find this third
we
zero.
don't find this third 0.
Of course, we are not.
Of course,
This
we are
third
not.
zero is just didn't disappear, right? So how can we find back our third zero?
How can we find back our third
How
zero?
can we find this third zero? Well,
How can we find this third
let's
zero?
rescale our space.
Let's rescale our
Y,
space.
a new variable which is epsilon
Y,
x.
a new variable which is
You
epsilon
plug
times
this into
x.
this cubic
You
equation,
plug
which
this
you
into
actually
this
find
cubic
y
equation, which you
cubed
actually
times y
find
squared plus
y
epsilon
cubed
squared.
times y squared plus epsilon
These
squared.
two equations are, of course,
These two equations are, of
equivalent.
course, completely
Long
equivalent.
as epsilon is not equal to zero, right?
Long as
Because if
epsilon is not equal to
zero,
zero, right? Because if
this
epsilon is equal to
rescaling
zero,
doesn't make any.
this rescaling doesn't make any
But now we still want to put epsilon
But
is
now,
equal to zero,
we
right?
still want to
Because
put epsilon is equal to zero, right? Because we want to know,
say
in the
when epsilon
limit,
is zero, can we find
say when epsilon is zero, can we find
to zero?
information? So we
Over
come
here,
to
can
zero,
we find three zeros?
over here, and we find three zeros.
Twice,
Plus
and the
zero
other
is
root is
zero
around
twice, and the other root is around one.
Well, in this new coordinate, we again
In this new
back
coordinate, we again back
to the
to
three
the
roots.
roots. Where the three roots.
Better?
Better?
Yeah. Well, continue.
Yeah.
The thing is,
Well,
the screen
continue.
is
The thing is, the screen is telling us to play.
Yeah, it seems, yeah. Yeah.
Hello.
Yes, it seems, yeah, I could hear you, but yeah, but your sound was a bit broken also. Yeah. Peter?
Now, it's okay for me to continue? It's okay for me to
Yeah, I think so.
yes, yes, I
Okay.
think so.
Yes, yes, I think so.
Okay. Oh, so you're not.
Oh, so
I
you're not.
okay, so already a couple of slides prepared.
Already a couple of slides prepared.
Hmm.
John, do you know what's going on?
Yeah, that's what
So, you know what's
okay,
going on?
she says you're okay now.
Okay, so you're back to slide 50.
Okay, so you're back to
Now,
slide 50.
now,
Um,
so we see here now, we
so
find
we
the
see here now,
we find our rescaled equation.
in our rescaled equation.
If we now undo our rescaling,
If we now
find
undo our
the third term,
rescaling, we indeed find the
1
third
over
term, which
epsilon.
is, or the 1 over epsilon.
Zero is a big zero.
This zero is
So-
a big zero.
Of course,
So,
when you put epsilon to zero, this
of course, when you put epsilon to zero,
solution goes
this
to infinity. That's why we
the
don't
solution
find
goes
it.
to infinity.
So
That's
we
why
take
we
epsilon
don't
as
find
point
it.
one, as we
So
did
we
in the
take
previous
epsilon as
slide.
point 1, as we did in the
See,
previous slide.
solution is
We
allowed.
indeed see the solution is allowed.
So, now rescaling our problem, we
Now,
again
rescaling
found
our
back all
problem,
our
we
information.
again found back all our information.
But does something happen? Does this also
So does
happen?
something happen? Does this also happen?
Does this also happen for ODEs? Can
Does
we
this also happen for
something more or less
ODEs?
the
Can we
same problems
more or
in
less the
ODEs?
same
Well,
problems in
So
ODEs?
look
Well,
to this.
yes.
we have
look
two
to this. We have
component
two
reaction
component
reaction
reaction
kinetics,
reaction
this is
kinetics,
sort
sorry. This is
a
sort of
limit of the original
a
model, which I
limit
started with.
of the original model, which I
U
started
dot
with.
is U minus U
U dot is U
plus
minus U
epsilon times P.
plus epsilon times
P
P.
dot is epsilon times U minus.
And P dot is epsilon times U minus. The epsilon is against.
So let us now rescale time.
Let us now rescale time.
Rescale time.
Then we
We actually
rescale
see that
time.
we can make
We
it to
actually
this
see that
equation,
we can make it to a
which is
different
of course
equation,
equivalent,
which
it's
is
epsilon times U
of course
prime,
equivalent. It's epsilon
U
times U
minus
prime
U plus epsilon
to
P,
U minus U
and P
plus
prime is U
P,
minus.
and P prime is U
These two
minus.
equations
These
are
two
equivalent.
equations are equivalent.
As long as epsilon is not equal to zero.
As long as epsilon is not equal
Of
to
course,
zero.
the idea is, can we
Of
set
course,
epsilon
the
to
idea is,
zero?
can we set
Still obtain
epsilon to zero and still obtain the
So
information?
let's put epsilon to zero in both
So let's
equations.
put epsilon to zero
I
in
will call
both
the top
equations.
one I will call
I
fast.
will call the top one I will
The
call
bottom one I
fast,
will call
and
slow.
the bottom one I will call slow, which will be a
So as I said, the systems are the same.
So as I said, the systems are the same when epsilon is not equal to zero.
There are three fixed points.
There are
One in
three
the
fixed
origin
points,
and two
one
around
in the
plus
origin,
minus one.
and 2 around plus minus
and they have
1.
different reduced dynamics. So
And they have different
systems are
reduced
equivalent,
dynamics.
they are the same,
Systems are equivalent, they are the
unless we
same.
take epsilon is equal to 1.
Unless we take epsilon equal to 1.
zero.
That's
That's
actually
actually
epsilon equal to 0. But that's actually what we want.
Let's
So
put epsilon to 0 and see what happens.
let's put epsilon to 0 and see what happens.
Again, this is the fast system.
So again, this is the fast system.
We
This
put
is the
epsilon
slow
to 0.
system. We put epsilon to 0.
So we get a fast reduced system.
So we get a fast
Which
reduced
is
system,
given by u dot
which
u minus
is
u
given
cubed.
by u dot is u minus u
And p
cubed,
is the constant.
and p
Because
is
the
the
derivative of p
constant.
is 0.
Because the
This
derivative
is,
of p
let's
is
say, a
0.
one parameter family.
This is, let's say, a one parameter family.
So for every c naught, we have
Over
the same
every p naught,
ODE,
which you have the same ODE which you need to say.
But if we now look at the slow reduced system, so
Then
set
now
epsilon
look
to
at the
0
slow
in this
reduced system. So
equation.
set epsilon to 0 in this equation.
Now we
What do
get
we get?
u minus u
Now we
cubed
get
is 0.
u minus u
We get
cubed
the
is
equation
0.
for p.
I get the equation for p. P prime is
So
minus
we don't get a one parameter family.
you don't get a one parameter
We've got a
family.
1D
This system.
differential.
You've got a 1D differential algebraic.
So the system which you start with, these two
So the
equivalent
system which we
equations,
start with, these two
and we
equivalent
take
equations,
epsilon to be 0,
and we take
instead of small,
epsilon to be 0 instead of small,
different.
here's something completely
But
different.
they're
But
both much easier,
they're both much easier.
which is what
Which
we want,
is
right? Because we want to make our
we
life
want, right?
easier.
Because we want to make our life easier by setting epsilon to 0.
So can we still use this?
So can we still use this Gaussian system and this slow
study,
reduced system
let's say,
to study, let's say, the full system?
here's the dynamics of the fast reduced
Here's
system.
the dynamics of the
So
Gaussian
for every
system.
constant
So
p,
for every constant
zero.
p,
fixed
point
point,
0,
plus
fixed
1,
point,
and minus 1 are
plus
stable
1
points.
and minus 1 are
So
stable
for every
point and
p,
0.
we
So
have
for
this
every
dynamic.
p, we have this dynamic.
The first
The first,
slow reduced system,
the
you see we
slow
have an
reduced
algebraic
system,
constraint,
you see
so
we have an
you
algebraic
can only
constraint,
be minus
so
1,
you can
0,
only be minus 1,
plus 1,
0.
and then
Plus
fixed
1,
points are exactly,
fixed points are exactly,
so minus 1 is subtracting,
so minus 1
0,
minus
0,
1 is subtracting,
0, 0 is subtracting, and 1, 1.
0, 0 is subtracting, and 1, 1.
One thing to notice at
One
this
thing
point
to notice
is that
at
the
this
slow
point
reduced system,
is that
this
this
over
slow
here,
reduced system, the system
is
over
only
here,
defined
is only
u
defined,
u
u
minus
minus
u
u
cubed is 0,
squared,
right? So it's
u
only
minus u
defined
cubed is 0, right? So it's
fixed
only
points of
defined
the fast
on the fixed points of the fast reduced.
So the equation,
So
dynamics over
the
here,
equation, dynamics over here,
and over here,
over here,
exactly
and
the
over
fixed
here,
points for a
it's
fast
exactly the fixed points for a fast reduced.
So, in the necessities, the shell shows,
Necessities, shell showed,
I that there is two simplified systems
let's say it's
containing information about the full system.
to obtain information about the full system.
Let's say you take the initial condition
Let's
over
say
here.
you take the initial condition
Not
over
on
here,
one
which is not on one
constraint, right? So we don't know
of
what
these
happens.
constraints, right? So we don't know what happens with
But
the
the fast
reduced
reduced
system,
system is defined.
but the
So
fast
let's say
reduced
the
system is
dynamics
defined.
becomes
So
like
let's
a
say that the
fast
dynamics
system,
becomes like
and
a
our
system,
block
and our
just moves
block just
This fixed
moves this fixed point.
on the fast. When it's on this fast reduced system,
When it's on this fast
the
reduced
slow reduced
system,
system is now so defined.
the slow reduced
So we can
system is
sort
now
of
so
signal
defined.
that the
So we
dynamics
sort of
is now
signal that
from
the
now
dynamics is
dominated
now
by the slow reduced
from now on
system.
dominated by the slow
So we
reduced
now
system.
start at this point,
So we now start at this point,
and we move down to minus 1 minus.
and we move down to minus 1 minus.
So the idea is very challenging.
The idea is
Yes, we can indeed
very
sort of
challenging.
combine this
Yes, we
picture
can
of
indeed
fast
sort of
reduced
combine this
system
picture of the fast reduced system telling us what happening
when we
beginning,
reach this
and when
manifold
we
of
reach
fixed points over
this
here,
manifold of fixed
which are
points
called
over here,
m not
which are
minus
called
for
m not minus
1
for
because it's around
m
minus 1.
not minus 1 because
We
it's
have
around
set
minus
epsilon
1.
to 0.
We have
When
set
we
epsilon to
arrive
0.
at this
So
manifold
when
of
we
fixed points,
arrive at this manifold of
the
fixed
slow
points,
reduced dynamics,
so that the
slow
slow
reduced
reduced
system
dynamics,
from that moment
slow
on
reduced system
determines
from that moment on
dynamics.
determines the dynamics.
So, we shall wrote this down in Turing.
And Michel wrote this down in Turing.
Here, so under some melt
Here,
conditions from this
Under some
manifold,
melt conditions,
under some melt
under some melt conditions
of this manifold over here,
of this manifold over here,
namely normally hyperpolicity, so
namely
you can
normally
have
hyperpolicity, so you cannot have
eigenvectors
eigenvectors from the
some melt
reactions.
conditions.
Under
The
some melt
system, so
conditions,
when we turn on
the Dürr
epsilon,
system, so when we turn on
as long as
epsilon,
epsilon is small,
it
it also has
some
some
small,
manifold,
it also
and
has some manifold and epsilon plus minus 1. So this manifold, what the student says, in the term epsilon, these manifolds over here,
they persist. So this M naught,
they persist. So this M naught,
and they
persist and
close, the old ones,
close, the old ones, they're also diffeomorphic.
and now, from now on,
And now, from now on, what we can also show is that all these manifolds are actually low, there is flow, of course they're not fixed points anymore for the complete system, but the flow is what we call locally invariant, so it will only move in a slow direction.
for this example, which we did over here,
For this example, which we did over here, because we chose it correctly, explicitly
so we already constructed the
So
M
we
naught
already
side around
constructed
plus or minus
the
1
M
and
naught
0,
side
which was
around
given by
plus or minus 1 and 0, which were given by u as plus or
U
minus
is
1.
0. And if you now
And u is
construct
0.
M epsilon,
If you now
not
construct
these
this M epsilon,
corrections when we
not
turn
so
on
this-
epsilon,
these corrections
you
when
will
we turn
see
on epsilon,
U is minus
then we
epsilon
see
p,
that u is minus epsilon
close to
p,
0,
which is
and the other
close
ones
to
are also close.
0, and the other ones are also close to 0.
So when you turn on epsilon,
When you turn on
manifolds
epsilon,
which are easy to find,
these manifolds
they're
which
not
are easy
exactly
to
the same
find,
anymore, but they are
are not exactly the same anymore, but they are in the vicinity.
also have a penny shot 2,
Also have a penny shot 2, and a
penny shot 3,
3,
but that
penny
first
shot
penny
3,
shot
but
2,
let
it more or less
first
tells you
penny
if
shot
you have
2,
this
it more or
manifold,
less tells you if
fixed
you have
point,
this
it is
manifold,
of course a stable
fixed
and
points,
unstable
it is of course
manifold,
a stable and
and they
unstable
also
manifolds, and they also
they're also.
they're also.
So penny shot 2 and 1 more or less
So penny shot
tell
2
you,
and 1 more or
yes
less.
you can set up to 0, and
Yes, you can set
all
up to
everything
0,
more or
and
less
yes,
stays.
everything more or less stays the same.
So let us skip penny shot 3,
And let us skip
and
penny
let's
shot
just
3,
do this thing.
and let's just do this picture. So
When we set epsilon to 0, we
when
sort
we
of have
set
these
epsilon to 0, we sort of have these two
systems, and when you combine them,
systems, and when you combine them, sort of
some of this. So if you start in the red
So,
region,
if you start in the red region, you first go vertically to
blue
the
line over here,
blue
M naught minus
to the
1,
blue line over here,
and then
M
you
naught
move
minus
down
1, and then you move down to X point minus 1.
start in the red region,
Start in the
first
red
move to
region,
M naught
you
plus
first
1,
move to M
then you
naught
move
plus
upwards.
1, then you move upwards to the point plus 1.
This is, let's say, for the
This is, let's say,
third system,
for
and
the
then
third, for the
0,
third system, and
now turn on epsilon.
0, let's now turn on
See,
epsilon.
everything
You
changes,
see?
but only a bit.
Everything changes, but only a bit. Let's redo this.
So I hope you can see this, but
I hope you can see
this
it.
red
So,
region.
what we have
So
seen
what
is
I've
red
taken,
region.
I've taken epsilon
So
to
what
be
I've taken,
0.05,
I've
so
taken
small.
epsilon to be 0.05, so small. I plot the pulse system.
Fixed points, they
See that these
change.
red dots, the
You
fixed
can
points,
nearly-
they change.
more or less you
You
cannot
can
see
nearly,
it.
more
We
or less
also
you
see
cannot
that
see it.
these
We also see that
lines
these used
and
to
are
be
slightly
straight lines,
different lines.
and are
They're
slightly
close to the
different
original.
lines. But they're close to the
Also,
original.
Red regions are
Also,
stable manifold.
Red regions are the
This line is
stable
stable
manifold.
This line
This
is
line is
also
the stable manifold.
persist.
This line
The
is
red
also
region
persist,
is more or less
because the
similar
red
to the
region is more or less similar to the red region.
Excuse me. But the main message here is
But the main message here is
our unperturbed system gives
our
us
unperturbed
deep
system
information about the
gives us
perturbed.
deep information about the perturbed
So
system.
by setting absolute
So
zero,
by setting
if you do
absolute
this correctly,
zero,
because our problem
if
is
we do
single
this correctly,
perturbed
because
height,
our
so
problem
we
is
need
single
to do some
perturbed
scaling,
height,
but
so
if
we
do this
need to do
correctly,
some
we can
scaling,
still
but if
find
we do this
information
correctly, we can still find
from the
information
from the epsilon is non-zero case,
from the epsilon is non-zero case
we still
by
can
setting
get
epsilon to zero. So we still can get approximately
setting epsilon to zero.
by setting epsilon to zero.
So,
So
I see that there are no questions at this
I
moment.
see that there are no
Are you
questions at this
still
moment.
with me?
Are you
on the correct
still
slides?
with me on the correct slides?
Yeah, let me.
If I hear nothing, I presume it's
If I hear
okay.
nothing, I presume it's okay.
Yeah, let me ask. Let me see. Let me ask them whether they are okay. Margaret, it's he wanted to find out whether you are on the same slide.
Yes, well,
Okay, yes.
Okay.
okay, yes.
Okay. Excellent.
So,
You are
this
now
was,
muted.
let's say,
So,
easy
You are
This
now
was,
muted.
let's say,
ODE
easy
example.
ODE example.
When I look, let's say, for stationary solution,
When I
what
look
I did
at
over
the
here,
stationary
for
solution, what I did over here, for the transition, we can of course change of PDE
now it will not
to
be
an ODE.
component, but there will
Now
be
it
6
will not be
components
two components,
actually.
but there will be 6
You can
components
still use this
actually.
ideal
You can still use this ideal geometrical synchronization theory.
One pulse,
practice.
two
One
pulse,
pulse,
traveling
two
pulse,
pulse,
traveling pulse.
traveling pulse. We can
Becomes
do
harder
it
in
in 2D.
2D.
It becomes harder in 2D, but we can still
This
use it
solution
as
is
a
spot.
This solution
This
is
is for the
spot.
spot solution because you didn't see
But
any
this
of
for
the
the spot
movies.
solution because you didn't see any of the
This now
movies.
means I only plot you
This
and
now
then use
means
a color
I
plot.
only plot
So
you and then
white
use a
means
color
you
plot
equal
of you.
plus
So
1,
white means
black
use
means
equal
you
to plus
equal
1,
minus 1.
black means use
So
equal to minus
use
1.
plus 1 over here.
So use plus 1 over here. Now two dimension is it's in this.
Here means that you use minus 1, so you
Here means that use minus 1, so use.
and don't show the P and the W.
And don't show the P and the W
spread out
because these are much more spread out and don't give us nice picture.
But I can use this geometrical
But I can
synchronization
use
theory
this geometrical
more or less
synchronization perturbation theory
construct
more or less to
all
construct
these type of solutions.
all these type of solutions.
And of course, we also have to do with
Because we also have to
stability.
do with
For this, we
stability.
use the Evans function.
For this we
And
use the Evans
so
function.
Evans function is a
And
one
so Evans function is a
The
one
zeros coincide with the
The
point
zeros
spectrum
coincide
of
with
the
the
linearization.
point spectrum
And
of
if
the
you have
linearization.
constructed, let's
If
say,
you
a
have
stationary solution,
Constructed, let's say, your
you
stationary
linearize,
solution.
you get an eigenvalue
You
problem.
linearize, you get an
This
eigenvalue problem.
Essential
This
spectrum.
eigenvalue will have
Spectrum.
essential spectrum.
Essential
Point
spectrum will be
spectrum.
okay for this.
Essential
problem,
spectrum
which
will be
is
okay
shown,
for this
But
problem,
now
which
we have to
is to show.
determine the point
But now we have
spectrum,
to
which is hard.
determine the point
For this,
spectrum,
we
which
can
is
use
hard.
The Evans
For this,
function
we can use
to prove
the Evans
linear
function
stability.
to prove that the
And
linear stability in the end.
I don't know why it says spectrum of
I don't know why it says spectrum of the issue.
So I don't say too much about this Evans function.
I don't
but
say
it's
too
a
much about this
tool
Evans function, but
which
it's sort of a tool
which gives you
which determines-
information about
which
the
gives
point.
you information about the point.
So let's say we use this tool.
So let's say we use
what
this
we
tool,
can derive.
and for example,
What is
what
one
we
pulse
can
over
derive
here, so this
is
is
for this one
U
pulse
component
over here,
again
so this
is
is
PW.
U component again and PW.
Assist.
U pulse
The parameters
assist.
are chosen such a way
The
that
parameters
we
are
can find
chosen
an
such a
X
way
which solves
that
this
we can
equation
find
of
an
this.
X which solves this equation of this.
That we can
Explains
find
the
an X
equation.
to solve this
So we can
equation.
find an X to solve this equation.
For this
And
solution, this expression
This
is also
solution,
positive.
this
So
expression
all
is
the
also
parameters are
positive.
It's
So
always
all the
case
parameters
right.
are positive. It's
Then
always
the
the case right. Then the solution.
Moreover, the width,
Moreover,
the distance between this front
Width, but the distance between this front
You are now unmuted.
You are now unmuted.
So is the sound back? Hello? Yeah. So, Margaret, can you hear now or? Hello?
The last message hasn't even done.
Yeah, we can hear you, but I don't know whether you can hear us. Okay. Yeah.
Okay.
So we can hear you. Peter, can you hear them?
Yes, I hear them, yes.
Yes,
Okay.
I hear them, yes.
Okay. So Margaret, can we continue? Margaret? Can we continue? Okay. Okay.
Yes.
Okay, that's
Continue. We can download the simulator and fill in the gaps.
okay. But you still have but how is the sound back or? Is the sound back? Yeah. Okay.
Okay, so I will continue, right?
Okay.
Yes.
I will continue, right?
We're talking all over the world, right? So it's
We're
awesome.
talking all over the world, right? So
Yeah.
It's awesome that this actually works.
Let's not be too critical.
Yeah.
Let's not be too critical
Yeah.
on the sound, right?
So we have a solution we can determine
We have a solution we can
Now,
determine stability.
final couple of
Now,
slides, we want
For
to
the
start
final
with
couple of
the
slides,
next
we want
one.
to start the outlet because of the next one.
We want to study interaction,
So we
which
want
I
to study
explained before, right?
interactions, which I explained
Can we
before, right?
derive this ODE
Can we derive this
describes
ODE? It describes
what's going
what's going on.
Organization group theory,
Organization
which is
group
real
theory,
hardcore PE
which is
analysis,
real hardcore
which is
PE analysis, which is
a long time to learn, so it's
a long
definitely
time to
too
learn,
much to
so
explain
it's
over here, but
definitely too much to explain
cooked up
over
in
here,
this
but
example,
cooked up
sort
in
of
this example,
gives the essence
sort
of
of
this real
gives the essence of this
So,
real
if you think of this ODE,
So, if you think of
x
this
dot
ODE,
equal to minus
x dot
1
is
minus
equal to
epsilon 2
minus
times x,
1 minus
we put
epsilon
in some
2 times
initial
x, and we put in some
if
initial
you say
conditions.
this is epsilon t,
If you
it's
say
again
this is
small,
epsilon
so
t,
it's smaller
it's
than 1,
again small, so it's smaller than 1,
smaller than 1,
it's smaller than epsilon,
you of
smaller
course
than 1.
know
You of course
x
know
naught will be in a fixed point.
x naught will be in
Let's
a
say-
fixed point.
For the moment,
Let's say-
for the sake of
moment
this
for
example,
the
we
sake
don't
of
know,
this
and we want to
example,
prove
we
that
don't
zero is
know,
fixed.
and we want to prove that 0 is fixed.
What can we do? Then we can use the
What can we
variation
do?
constants
Then we
formula,
can
right?
use the variation
and solve
constants
this
formula,
equation.
right, and solve
X
this
of t is
equation.
now given by e to the
X
power
of
minus
t is now given by e to the power minus
plus this
condition.
Now
plus
we
this
want to
in-
make some estimates.
Now we want to make some estimates.
So we introduce
So we
1
introduce
t as the supreme number
1 t as
e
the
to the power
supreme
t
number
times x t.
e to the power
Now
t
we multiply the
times
equation
t.
by e to the power
Now we
t.
multiply the
We
equation
get
by e
the
to the
following
power t.
estimate.
We see we
E
get
to
the
the power
following
t times
estimate
x t
e to the power t times
less or
xt
equal than
should
a
be
naught
less or equal than
plus
a
epsilon
naught
times t.
plus epsilon times t.
We now have an s like
So we now have an s
because we have an issue, right?
because we have an
this
issue,
secular
right?
term,
Because we have this
because of the
secular
t
term,
so we
because
cannot
of the
use
t
this
over
estimate
here,
for all t,
so we
right?
cannot
Because
use
this
this estimate
will
for
blow
all t,
up.
right? Because this estimate will blow up.
Let's now sub over all t,
Let's now sub over
and
all
then we
t,
can actually rearrange
and then we
everything
can
a little
actually
bit. So what
and
we can
rearrange
show
everything a little
is
bit. So
our
what we can
Freeman
show is
is
actually
less
our
or equal to
Freeman
a naught
is actually
over
less
1
or equal
minus
to a
epsilon
naught
times
over
tau.
1 minus
And
epsilon
here you again
tau.
see the problem,
Here
right?
you again see
When
the problem,
tau
right?
becomes 1 over epsilon
When
naught,
tau
this
becomes 1 over
estimate
epsilon
is
naught,
solved.
this estimate is solved.
And if you go back and write this in our original
And if you go back and write this in our original coordinates,
it's over here, we actually have a bound on
so
x
here we actually have a bound on xt. So xt is less or equal to 2 times e to the power minus t
for
times
some
the
interval,
condition for some
which
interval,
allows us
which allows us,
this term doesn't
which
go.
we make that this term doesn't go
So
in.
let's do this in a picture.
So let's do this in a picture.
Let's say this is the real solution of the
Let's
line.
say this is the real solution of the line we now take an approximation
decline, and at one moment this approximation
decline, and at one moment this approximation goes down with
at this point, what we do,
so at this point, what we do,
some time point to say, okay,
some time
from
point
this
to
point
say,
on, our
okay,
approximation is
from
not
this
valid
point on,
anymore.
our approximation is not valid anymore.
And then the idea is,
The idea of
at this
realization
point we
is,
choose a new initial
at this
condition.
point we choose a new initial
So we're
condition.
going to solve the same ODE,
So we're
but
going to
now
solve the
with
same
initial
ODE,
condition at this
but
time
now
step.
with initial condition at
This
this
initial
time step, with this initial
So,
condition.
it is at time
This
t
is
star,
at time
which was
t
this one
t
of
star,
not
which was this one of
choose a
two
new
epsilon naught.
initial condition
Choose a
A1,
new
which we actually
initial
choose to
condition
be the endpoint of our
A1, which we
previous
actually choose to be the endpoint of our previous
A1
approach.
is really
A1
this point
is really
over here.
this point over here.
So we now solve this new ODE, right?
So we now solve the new ODE, right?
But
So
now
we
we
have the
have
same
the
ODE,
ODE, so at
but
time
now we
1
have a
over
new
2
initial
epsilon
condition.
naught,
So
we
at
are
time
at
1
A1.
over 2 epsilon naught, we are
Now,
at
of
A1.
course, we can repeat the procedure.
Now, of course, we
from
can
the previous
repeat the
step, right?
procedure
We
from the
integrate this,
previous step, right? We
multiply
can
the e
integrate
to the
this,
power
multiply the e
minus
to
t,
the power minus t,
you multiply by e to the power minus
you
t,
multiply by e
and
to
we
the
can
power
get
minus t, and we can get s.
If we do this, in
If
the
we do
second
this,
time interval, we now
in the second
can
time
show that
interval,
x to the power
we now
t
can
is
show
equal
that
less than
x to the
4
power
times
t
e to
is
the power
equal
minus
less
t.
than 4 times e to the power minus t.
And when this
And
approximation
when this approximation, excuse me,
goes AWOL again, when the second term
goes
goes up,
AWOL again when
we
the
again
second term
repeat
goes
the
up,
procedure, so
we
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 choose
again
A2,
repeat the procedure so we
the
choose
endpoint.
A2, which is
So
the endpoint.
we just keep on
So
repeating this,
we just keep on repeating
and
this.
what we in the end find is that we
And
have
what
a
we
bound
in the
on
end find
xt
is that
for
we
all
have a
time
bound
t.
on xt for all
Given
time
over
t.
here, it's 2 times A
It's
naught,
given
2
over
times
here, it's 2 times
power
A
minus
naught
t, 1
times
minus 2
e to the
epsilon
power
naught.
minus t, 1 minus 2
But it's
epsilon
epsilon
naught.
naught was this bound,
But it's epsilon naught is
epsilon
bound
t, right?
on this epsilon t,
So,
right?
as long as this epsilon naught is
As long
smaller
as
than
this
2,
epsilon
then
naught is smaller than 2, then the
see that we have a
intersection
net
of 2,
contraction over
see
here.
that we have a net
So
contraction
we have
over
now
here.
proven
So we have now proven
that
that circle is perfect.
you can do this in a picture.
You can do this in a picture.
This was the first one, right? We
This
choose
was
A naught.
the first one, right? We choose
Approximation
A
goes
naught.
wrong, so we choose
The
an
approximation
A1.
goes wrong,
Different
so
one.
we choose an A1. We choose
You
a
have now
different
again
one.
an approximation.
You have now
The
again
moment
an
it goes
approximation.
wrong,
The
choose a
moment
new
it goes
initial
wrong,
condition.
we choose a
And
new
see,
initial
here we've
condition.
got a recent
And see,
approximation.
here
and
we've
if
got
you
a
have
recent
time to infinity,
approximation, and if
see
you
that
have time to
indeed
infinity,
approaches the fixed
you see
point.
that it indeed approaches the fixed point.
Now with this RG method,
Now
now
with this RG
for the
method,
simple ODE
we now
example,
prove
that 0
for the
is fixed.
simple ODE example that 0 is a fixed point.
The PDE, you can also do this. It's a little bit
You
more
can also do
complicated.
this. It's a
What we
little
can
bit more
do,
complicated.
if this is PDE
What we
over
can
here,
do, if this is the PDE over here,
one-dimensional, you can actually derive
one-dimensional,
equations.
you can actually
For the
derive
front,
equations.
For the
Let's say
back,
for the front,
the equation is given
the
by
back,
this.
the
Now
equation
we
is
can see
given
we
by
can
this.
eliminate one of
Now we can
those.
see we can actually
So we
eliminate
can
one
get
of
an
those.
equation which only
So we can get an equation which only
determines the difference.
determines the difference.
This is an ODE.
This is an
Describes
ODE
how this PDE
which
works.
describes how this PDE
And then of
works.
course we want to check whether we
Then
want
of
to
course we
compare.
want to check whether we
Right.
want to compare.
So here
whether
we
do it
I
right.
overlay the PDE
So here
simulation,
I
which are the blue
overlay
ones
the
and
PDE
the red
simulation,
ones.
which are the
I
blue
overlay
ones
this
and the
with
red
the
ones.
ODE,
I overlay
black
this with the
line.
ODE,
and we
which
see
is the black line.
we go inside.
And we see they coincide.
If our solutions are divergent, we
If our
see we have some
solutions
problem
are
over here, right?
divergent, we
Because
see
we
we
made
have
a
some
small
problem over
mistake,
here,
so
right?
after a
Because
long
we made a
time,
small mistake,
small
so after a
mistakes
long
gives
time,
us some
a small
contribution.
mistake actually gives us some contribution.
But in general, this ODE
But in general, this
approximation
ODE
works.
approximation works,
And we
system.
can prove that it works.
and we can prove that
simulations
it works,
are accurate.
and a simulation.
And we can generalize also this theorem.
And we can generalize also this theorem to
Not
the
the two fronts, but let's say the
dynamics, not the two fronts, but let's say to do it with 12.
So this was more or less
This
everything
was
which I wanted to
more or
say.
less everything which
So
I wanted to
let's
say.
do a summary of what I
So let's
thought
do a
about
little summary
what I
of what I
talked about
thought
today.
about
So we
what
started
I
with a
talked
little
about
bit of
today.
Turing
So we started
instabilities,
with a little bit of Turing instabilities,
and then I changed from small
and then I
amplitude
changed
dynamics
from
to
small
complex
amplitude
dynamics
dynamics to complex dynamics
particular
for this
system.
particular
It shows you results
system.
of existence,
It shows you
stability,
results on existence,
and
stability,
then in the end I gave you two
and then in the end
simplified
I gave you
examples
two simplified
to
examples
exemplify how these methods are
to
actually
exemplify how these methods are actually working, which I use to study this.
And at the moment,
I'm
I'm one dimension interaction, right?
just started one
Now
dimension
starting to
interaction,
think
right?
about how can we do
Now starting to
simulation.
think
now
about how
unmuted.
can we do
So let's
simulation.
say that we have two traveling
So
spots
let's say that we have two traveling
which
spots
hit each other.
which actually hit
How
each
do
other.
they interact?
How do they interact?
How does this change, let's say, when we change
How
the
does
angle?
this change, let's say, when we change the angle of collision?
Also interesting, right? We have this
Also
spot
interesting, right?
traveling,
We have
but we
this
also have
spot
this stripe
which is
solution.
traveling, but we also have this stripe solution, which is not
Now
known.
what happens if we shoot it
Now what happens
to
if
the
we
stripe? How
shoot
do they
it
interact?
to the stripe? How do they
And
interact?
as a final picture,
And
there
as
is
a final
12,
picture,
sort
there
of
is movie 12,
talks a little
it sort
bit
of
of shows a little
talks a
bit
little bit
simulation of
shows a little
what
bit
happens
the
when
simulation
two
of what happens when two of these spots.
and that was it for today.
And that was
And
it
I'm
for
sorry I went
today.
a little bit over
And
time,
I'm sorry I
but
went a
there
little
were
bit
some
over
loose
time,
connections.
but there were some loose
Thank you
connections.
so much.
Yeah, thank you. So, Investor Ghana, do you have any questions?
I think we have to digest. I think we have to digest first. We missed some sections of it because of
Okay.
sound.
So I'll have it up on the website by later today. So yes.
That way we can look at it again. That way we can look at it again and watch the movements. Were far too slow. Movements were far too slow. We couldn't even
Okay.
get one loaded.
Okay. Yeah. Again, I think the issue is the internet is a bit of the internet connection. That's the reason why.